Have you ever heard of a star so dense that a single sugar cube of its material would weigh 1 billion tons on Earth? These are neutron stars, the remnants of massive stars that have gone through spectacular deaths. Today, we'll explore these incredible cosmic objects, their formation, properties, and mysteries. Welcome to our channel, where we uncover the wonders of the universe. Don't forget to hit the subscribe button and join us on this interstellar journey. Section 1: How neutron stars form. Neutron stars are born from the dramatic deaths of massive stars. But not every star can become one. Only stars with a mass between 8 and 25 times that of the Sun have the necessary conditions to form neutron stars. Stars with less mass end their lives as white dwarfs, after shedding their outer layers to form planetary nebulae. When a massive star runs out of nuclear fuel, its core can no longer generate energy to counteract gravity. This causes the core to collapse, triggering a supernova explosion, provided the star's core has sufficient mass. During this collapse, the extreme conditions force electrons and protons to combine into neutrons, a process called electron capture. What remains is a dense core made almost entirely of neutrons, hence the name, neutron star. The collapse continues under immense gravity, but quantum mechanics prevents the core from being crushed entirely. Neutrons, governed by the Pauli exclusion principle, resist being compressed into the same quantum state. This resistance generates degeneracy pressure, a quantum force that counteracts gravity. The balance between gravity and degeneracy pressure stabilizes the neutron star. If the star's mass exceeds a critical limit, called the Tolman-Oppenheimer-Volkoff limit, about 2 to 3 times the mass of the Sun, degeneracy pressure can no longer resist gravity, and the star collapses into a black hole. Neutron stars, therefore, exist as a delicate balance between collapse and resistance, forming one of the densest objects in the universe. Section 2: Unique properties of neutron stars. Neutron stars are more than just incredibly dense objects. They are also some of the most dynamic and diverse celestial bodies in the universe. Let's explore their unique properties, including pulsars and magnetars, and the extraordinary conditions that lead to their formation. The extreme properties of neutron stars. Neutron stars are unmatched in their density and gravitational strength. A neutron star's surface gravity is so immense that, if you were to drop an object from just 1 foot above the surface, it would hit the ground at over 4 million miles per hour. Their cores are even more extreme. Scientists estimate that the pressure inside a neutron star could compress matter into forms never observed on Earth, potentially creating exotic particles or even quark matter. In addition to their density, neutron stars often exhibit extremely strong magnetic fields. While typical neutron stars have magnetic fields trillions of times stronger than Earth's, some neutron stars push this to the extreme, which we'll discuss in a moment. Pulsars, beacons of the cosmos. Pulsars are a specific type of neutron star that emit beams of radiation from their magnetic poles. These beams are powered by the neutron star's rapid rotation and its intense magnetic field. If the magnetic axis is misaligned with the rotational axis, the radiation sweeps through space like the beam of a lighthouse. When this beam crosses Earth's line of sight, we observe it as regular pulses of light. Not all neutron stars become pulsars. Several conditions must align. First, the neutron star must have a strong magnetic field and spin rapidly after its formation. Over time, pulsars gradually lose rotational energy, which weakens the radiation beams. However, in binary systems, a pulsar can accrete material from a companion star, spinning up to extreme speeds and becoming a millisecond pulsar. These pulsars can rotate hundreds of times per second, and are among the fastest spinning objects in the universe. Magnetars, the magnetic monsters. While most neutron stars have strong magnetic fields, magnetars take this to another level. Their magnetic fields are up to 1,000 times stronger than those of typical neutron stars, making them the most magnetic objects known in the universe. This incredible magnetic power is thought to arise during the formation of the neutron star, possibly influenced by a combination of rapid rotation and a pre-existing strong magnetic field in the progenitor star. Magnetars are known for their dramatic and often violent behavior. They occasionally release massive bursts of gamma rays and X-rays, known as magnetar flares, which can be so powerful that they disrupt Earth's ionosphere from thousands of light years away. One such event, in 2004, originated from a magnetar about 50,000 light years away, but still affected radio communications on Earth. The mysteries of their formation. Why do some neutron stars become pulsars, while others become magnetars? The exact conditions remain a mystery. Scientists believe it could be related to the initial mass, rotation rate, or magnetic field of the progenitor star, but the details are still unclear. Additionally, not all neutron stars exhibit pulsar or magnetar behavior, and many become quiet neutron stars, emitting little detectable radiation. The cosmic laboratory. Despite these unknowns, neutron stars offer a unique laboratory for studying the universe. They challenge our understanding of physics, from the behavior of matter under extreme pressure to the mechanisms that drive magnetic fields and high-energy emissions. Pulsars and magnetars are just two fascinating examples of how diverse and dynamic these stellar remnants can be. Section 3. The mysteries of neutron stars. Even though neutron stars are some of the most studied objects in astrophysics, they continue to baffle scientists with their enigmatic nature. These dense remnants of stellar explosions pose questions that challenge our understanding of physics, the universe, and even reality itself. Let's dive into some of their greatest mysteries. What lies inside a neutron star? One of the biggest unanswered questions is the nature of a neutron star's core. We know that the outer crust consists of a lattice of atomic nuclei and free electrons. But as we move deeper into the star, things become far less certain. Under the immense pressure, nuclei dissolve, and neutrons dominate. But what happens in the very core? Some theories suggest that neutrons may break down into their fundamental components, quarks, forming an exotic state of matter called quark-gluon plasma. If true, neutron stars could be the only places in the universe where such a state exists naturally. Other possibilities include strange matter, a hypothetical form of quark matter composed of strange quarks. This exotic matter could drastically alter the properties of neutron stars, such as their mass limits and radii. Unfortunately, the extreme conditions inside these stars make direct observation impossible, leaving us with only models and simulations to explore these ideas. The puzzle of fast radio bursts, FRBs. Fast radio bursts, or FRBs, are powerful, millisecond-long flashes of radio waves that originate from faraway galaxies. While their exact cause remains unclear, some scientists believe that they could be linked to magnetars, neutron stars with ultra-strong magnetic fields. Magnetar flares could generate these bursts, but the exact mechanism remains elusive. Why are FRBs so bright? Why do some repeat, while others don't? These are questions that remain unsolved, and keep researchers actively investigating neutron stars' connection to these phenomena. Why do neutron stars have such strong magnetic fields? Another enduring mystery is the origin of neutron stars' intense magnetic fields. While it's clear that the progenitor star's magnetic field plays a role, the process by which it becomes amplified during the star's collapse is not fully understood. One theory suggests that the rapid rotation of the core during the collapse creates a dynamo effect, amplifying the magnetic field. But why are magnetars' fields so much stronger than those of ordinary neutron stars? The answer remains unknown. How do neutron stars evolve over time? Neutron stars change as they age, but many details of their life cycles remain unclear. For instance, why do some pulsars suddenly glitch, experiencing abrupt changes in their rotation rate? These starquakes might be caused by shifts in the crust or movements in the superfluid interior. but the exact mechanisms are still debated. Furthermore, the eventual fate of neutron stars raises questions. Do they cool into inactive, undetectable remnants? Or do interactions, such as collisions in dense star clusters, lead to their transformation into something entirely different? The discovery of neutron star mergers producing gravitational waves has opened a new window into their late-stage evolution. But much remains to be learned. What we've yet to understand. At their core, neutron stars challenge the limits of known physics. They push theories about gravity, quantum mechanics, and the behavior of matter to their extremes. Each new discovery about these enigmatic objects, whether it's a new type of pulsar, a magnetar flare, or a gravitational wave event, reminds us of how much we still don't know about the universe. Neutron stars are cosmic laboratories that challenge our understanding of physics and the universe itself. From their extreme density to their powerful magnetic fields, they are a testament to the incredible diversity of objects in space. Thank you for watching. If you enjoyed this journey into the world of neutron stars, give us a thumbs up and subscribe to our channel for more cosmic content. See you next time.